What is radioactive decay? Radioactive decay is a natural process where unstable atomic nuclei lose energy by emitting radiation to become more stable. This occurs when there is an imbalance between protons, neutrons in the nucleus, leading to the release of alpha particles, beta particles, or gamma rays. The rate of decay is measured by the half-life, the time it takes for half of a radioactive sample to decay. Substances with shorter half-life decay faster and are less stable, while those with longer half-life, like uranium-238, can persist for billions of years. Radioactive decay is vital in fields like medicine, energy, and archaeology, with applications such as cancer treatment, nuclear power generation, and carbon dating. However, managing radiation risk is crucial due to its potential hazards.
The purpose of this project is to see how much iodine is left after a few days of its decaying by using radioactive decay method. This method is using the change of mass of the substance after leaving it for a period of time. Then, the radioactive atom will decay or disintegrated into atoms of other elements. With this, we can calculate how much mass the radioactive substance has left. The formula is dA over dt is equal to negative Ka. Now, I will briefly explain on how we get dA over dt equal to negative Ka. First, integrate 1 over A dA equal to negative integrate K dt. Then, we get ln A equal to negative Kt plus D. Then, we multiply both sides with E to eliminate ln. Finally, we will get A equal to e to the power of negative kt plus d. Let's move to the meaning of each symbols in this equation. At represents remaining quantity of a certain radioactive substance. dA over dt represents rate of change of the mass. T is for time and K represents for decay rate. Let's move to our problem statement. Dr. Hidayah is a scientist. She wants to determine the iodine mass after 30 days. The initial mass of an iodine was 360 grams and the half-life of the isotope is 12 days. She knows that the amount of iodine that the present at time t is given by the equation. At equal to Ce to the power of Kt, where C and K are constants.
So here is the problem solution. Based on the given equation, At equal to Ce power of Kt, since the equation states that the initial mass is 360 grams, so we can conclude that A0 equal to 360. By the given information, we can find the value C by substitute T equal to 0 and A equal to 360. Since E power of 0 equal to 1, we get C equal to 360. So now, we get A equal to 360 E power of Kt. So now, we need to find the half-life by substitute T equal to 12 into the half-life formula. And we get the remaining amount of the substance on the day 12, which is 180 grams. By using the information of half-life, we can find the value of K by substitute T equal to 12 and A equal to 180 into the equation. By doing the simplification, we get K equal to negative 0.05776. And now, we get the equation that represents the amount of radioactive isotope remaining at any time t, which is A equal to 360 E power of negative 0.05776 t. Now, we need to find the iodine mass after 30 days. By substitute T equal to 30 into the equation that we derived just now. And we get the amount of iodine
after 30 days equal to 63.6439 gram. Thus, the iodine mass after 30 days is 63.6439 gram.
To conclude, the reduction in iodine's mass from an initial 360 grams to 62.6439 grams over a period of 30 days occurs due to its instability, which is characterized by a relatively short half-life of only 12 days. This decay process demonstrates the inherent relationship between the half-life of a radioactive substance and its stability. A longer half-life corresponds to a greater stability. For instance, uranium-238, which is one of the most stable radioactive substances known, has an extraordinarily long half-life of 4.47 billion years.